通过这个报告，但是隆重的推出就是像是2位教授。那么一个呢，我们特意请了清华大学的陈金教授，他是北京生物芯片中心的主任，也是长江学者，请他来给我们做主持。然后呢，就是我们这个报告人的背景，我相信大家都已经知道了，对吧？应该说，我前面可能有一些背景，这个龚老师已经可能跟大家做了一些介绍。那么希望大家能够今天能够跟我们的这个诺贝尔奖得主能够有一个这个很好的交流，好吧？就是我因为在这里呢，就是我只是先简单的说几句。那么我同时我也希望大家，因为今天来的人学生特别多，大家注意会场的秩序，然后待会儿提问啊什么的，大家最好是能够表现这个能够充分展现我们华中科技大学老师和学生的这个风貌啊。我们现在看来很热闹啊。OK， 要不我下边我们是不是因为我们可以开始应该，我们先请那个还有7分钟，我们要等吗？不等吧？OK， 我们的这个会议组织者就是学校要求我们要准时开始。那好，我们再等几分钟，好不好？因为还有几分钟。因为我们这次这个报告是这样，既是我们生物医学光子学这个中心的顾问委员会来组织的一次会议，同时我们也纳入到我们学校的人文讲座。对，刚好在利用这个机会跟大家，实际上这好像是1250次第是吧？对，像是我们学校的人文讲座，在这个杨叔子院士这个倡导之下，现在已经进行了这个1250次。所以应该来说也是，明天是那个Britton Chance 教授，他是做第1251次这个报告。OK， 这样我顺便借这个机会啊，也介绍一下我们这个来宾。I would like to speak English. Since before I just give a very brief introduction to the background of this talk. This is 1025th lectures, special lectures in this university. So the honorable Aaron CiechanoverWhy, you're going to take this the 1250th lectures. We call 人文讲座. It's I don't know how to Chinese in English. It could be art lecture. Yeah. Humanity. Okay, humanity lectures. It's a series humanity lectures. 我下边给大家介绍一下我们到会的这个贵宾啊，要不我看我怎么介绍那边是我们的 Dr. Britton Chance from University of Pennsylvania. I would like to introduce you. Dr. Chance. Dr. 达旋冯达旋校长。Dr. Feng from University of Texas, Dallas, and Dr. Goodman also from the University of Texas, Dallas. And Professor Richard Howard, from Canada. And Professor Stephen Downs, and he is the CEO of Main Infrared Biomedical Engineering Foundation. 然后 OK，this 这边是我们的姚建全院士 from 天津 University 天津大学。我们下一位是我们的宋瑞珍 Professor 宋瑞珍 from 台湾成功大学。我们下一位是Oliver 何成 from America。我们还有这个Dr. Shokanyaka from University of Pennsylvania。OK。那么我想估计时间差不多，我们下边还有一位就是我们的会议的主持人，这个 who is going to chair this lecture。it's 郝晨 ，OK， 我们陈大律师，他是陈律师陈德印 ，OK， 可能他的背景，如果我说英文，大家不一定理解，我还是 I better speak Chinese to tell his background， 因为如果是只是介绍他的英文的话，看大家是不是知道啊 ？He's the partner of K&L and Gates，right？ 他实际上是就是有一个叫做 K.L. 盖茨，就比尔盖茨的父亲，这个盖茨大家注意啊，是这个律师事务所的大律师，大家可以想象，反正连上盖茨的名字大家就知道了，对吧？OK， 是。那我们下边就是请我们的主持人，我们的清华大学的陈金教授，陈老师。OK。我们陈教授会把这个我们今天的 speaker 这个情况给大家做一个介绍，好吧？谢谢。
Good evening, dear guests, ladies and gentlemen. I'm honored tonight to introduce you the world famous person from the post I can figure out easily, the Nobel laureate, Dr. Aaron CiechanoverWhy. Aaron was born in Israel, and he received his formal training for undergraduate and PhD MD from the Technion in Haifa. And he has gone through his medical training from Hebrew University School of Medicine. Many people may think that a small country like Israel, how could they produce a Nobel laureate? And indeed, this is a legend. Aaron received his training there, and he discovered the mystery of ubiquitin proteome pathway, which regulates the degradation of proteins and recycling in the cell. And because of this, he was awarded year 2004 Nobel Prize, together with his supervisor, Dr. Aaron CiechanoverWhy. And from today's meeting, we shared our experience together by hearing what his suggestion to this very university. We learned that he highly regards the postdoc training and graduate training in different universities and even more different continental. And his experience postdoc 5 years almost in States at Whitehead Institute and MIT is a good example. And his background is mixed. He is an outstanding researcher, but also he is a very good surgeon. And not only that, he has done researches in quite different fields. For his postdoctoral training, he has studied subject that is the ion uptaken into the cell by the transferrin receptor, which is very different from what he has awarded Nobel Prize for. And when he finished his postdoc training, without hesitation, he decided to go back to serve his country. And I know sometimes how hard to make a decision like this, because we have also been trained in Western countries. Given my own experience, 6 years in Britain, 6 years in the States. And come back eventually to serve your own nation and country, you deserve it. I'm not going to read how many prestigious awards he has won in the past years. Nobel Prize is enough. But I'm not going to talk about this by introducing him. By going through his wonderful introduction, I have clarified with him just in our dinner time. I want to share with you, although, Aaron, believe me, in China at this stage, people may not believe you, but I still will tell you the true story. At this stage, almost every university in China encourage you very highly to publish papers in very, very highly ranked, so-called SI ranked journals. And given my own situation in Tsinghua University, a PhD must publish 3 English papers before he or she can go for defense, or a single paper with SI impact factor not greater than 5. Be honest, before I come back to China, I don't know what is impact factor. And I was so amazed when I talking to my colleagues in Tsinghua, they can recite the impact factors for many journals. That really is amazing. But now I'm one of them. I can remember many journals' impact factor. But how many do you know in what journal Aaron has published his paper, the paper that make him famous worldwide for Nobel Prize? The magazine, the name is called Biochemical and Biophysical Research Communications. This is the kind of paper that I said that my student has to publish 3 before they can get a PhD degree. So he said something very, very philosophical. He said, it doesn't matter where you publish your scientific discovery. What matters is what you are going to or you have published. So if anything after his lecture we can take away, this is one thing I think that especially students, you should think about this. The second thing, and the last thing, before I wrap up for the introduction, which I think very important, is Aaron, he has said something very touching when he got his Nobel Prize. He said, it's an honor for Israel, showing that even a small country, still it can make it. So it doesn't matter if it's a big country or small country. It doesn't matter if it's a famous magazine or if it's a not quite famous magazine. As far as your scientific discovery is true, is important, which will impact, even in the long run, people will know you sooner or later. So it doesn't matter, especially when you are young. So let's pay attention to his wonderful talk. And Aaron, please.
Good evening. I have to apologize for two things. One, I'm going to take off my coat. And two, I'm not speaking Mandarin. So you will have to bear with me in English. So what I'm going to try to do with you today is kind of floating a little bit between personal experience and science, and though don't mislead yourself for a single moment that I have any secret in my pocket for success, or I can show you the way to Stockholm. There is no way to Stockholm. So I would like first to start with two personal notes. The first one, it is my third visit to China. And I suspect that I will have to increase the frequency of my visits here. Otherwise, in a few years, you will not invite me anymore. And the reason is that this country is doing fascinating progress, unbelievable, catching up with the West in an unbelievable pace. And in a few years, you will not need any one of us, not for advice, not for consultation, not for scientific boards, not for nothing. You will be on your own, and maybe you will go the other way to big America to tell them how to do what. It's truly a fascinating country. The second personal note has to do with Britain chance. And I must take a few minutes to tell you about my own relationship with Britain. Actually, I met him the first time yesterday. And until yesterday, he was for me an imaginable icon. And when one goes on a career track, there is always the balance that one has to decide how much he wants to do on his own and how much he wants to imitate and to be like others. And I, during my medical studies, somehow stumbled on one of the most beautiful pieces of professions, which is called biochemistry. And in biochemistry, you gradually learn, I wouldn't say to admire, but to really learn and to have some lights at your tunnel. And these lights are basically names of people that are the founding fathers, the true founding fathers of fields. And among those names, several came up, obviously. One of them is Fritz Lipman, for example, the discoverer of coenzyme A and other many important discoveries. Another one is Konrad Bloch, Fyodor Linen. People that basically, if you collect these 5, 7, 8 names, you don't need to go any farther. You have the entire biochemistry in your hands. Complete biochemical pathways put together. And among those names, one of the most prominent one, and the group was not too big, as I can tell you, only 5, 6 people, was obviously Britain chance. And Britain popped up in many ways. Britain popped up once you're studying a very basic phenomenon, and that's how we convert our foodstuffs into energy, into the one single coin that we are using at energy, which is called ATP, or adenosine triphosphate. For me, adenosine triphosphate is like a second brother because we use it all the day in order to degrade proteins, and I'll get back to it. But the problem is how we take meat and proteins and lipids and carbohydrates and convert them into one single coin that allow us to keep our body temperature constant at 37 centigrade, to move our muscles, to pump blood, to take air, to expire air, to do everything. There is one single common molecule that allows us to do it, and that's ATP. We are living on energy, and energy must be transformed and produced, and Britain chance clearly belongs to the tiny small group of people that made this major discovery in biochemistry available to all of us. But then Britton Chance popped up completely from another angle. He's like Dr. Jekyll and Mr. Hyde. I mean, you cannot escape him. He popped up with something that for us is taken for granted, that enzymes work with coenzymes. I mean, how else? How else transaminases will work without pyridoxal phosphate? And how else dihydrogenases will work out without NADH and NADPH? It's so clear for us that enzyme is just a scaffold to reduce energy. But otherwise there is a chemical reaction that the enzyme catalyzes. And for catalysis, the enzyme needs a coenzyme in order to transform the substrate. And it was another giant, Hugo Theorel, with whom Britton worked in Sweden, that discovered to us this awfully simple thing, that there are coenzymes that must work with an enzyme in order to catalyze the numerous reactions that we are all catalyzing every moment in our body while you are sitting here and listening to my nonsense. So here came the Theorel chance theory paradigm. I mean, so simple. So until yesterday, I didn't believe that Britton existed at all. For me, he was somebody in the temple of giants, and all of a sudden I discovered a wonderful human being with whom I just started to chat. And we chatted not only on science, but of something that is as equally important, and that's the history of science. And Britton has a secret that he probably will not tell you, and that's the secret of longevity. And in this secret, there is something embedded. And what is embedded in the secret of longevity is that you had the chance to recognize personally and to know personally all those that even now, after I recognized and met Britton yesterday, for me are still icons. Because I haven't met most of these people. I haven't met Linen, I haven't met Bloch, I haven't met all the founders of the field that I'm living on these days. But Britton did meet them. And the important lesson in history of science that we should all remember, and I try to educate my students on this lesson, that many students have the feeling that once they walk into the lab, that is the moment that science is being born. And the moment that they leave the lab is the moment that science either dies or go with them. And we don't appreciate, or many of us don't appreciate, the very simple fact that we are all living in a continuum. And we are just contributing our small, tiny building block to this wonderful world of knowledge. We are all living in one community. Now we share the knowledge via much faster devices that we used to share it beforehand. We don't wait anymore for 2 months for a journal to hit the library. We just punch the internet, the PubMed, and the journal, and the article pops up. But nevertheless, the basic principle of this community is still the same. Sharing of knowledge and building it gradually, step by step. And there are very few of us that can be proud that their contribution to science is measurable in a very prominent way. And Britton clearly belongs to this class of giants. We have discussed today during the board meeting, the first board meeting of Britton Chance Center, the idea of interdisciplinarity, that it's not enough anymore these days, or it's impossible anymore these days to come to the lab and to work alone. We need lots of help of colleagues around us. Biologists need bioinformaticists, they need X-ray crystallographers, they need mathematicians, they need physicists, people that are expert, that have hands-on imaging, very sophisticated methods of imaging. Britton popped up yet in a third way, and that many years ago. Because when you look for the name of Britain, you will find it everywhere. You will find it obviously in classical biochemistry, as I told you, in ATP generation, in coenzyme catalysis, but then you can find it in photonics, in biophotonics, in development of modern imaging system. And there is no doubt that imaging is our future, because so far what biochemists did, they took cells and they broke them open, and they took the different proteins and they purified them, and they wanted to believe, which may be right or may be wrong or probably is partially right, that these isolated purified proteins behave in the test tube exactly like they behave in the intact cell. But the only way to know what's going on is to image a live cell and a live organism. And Britain is clearly identified again with major breakthroughs in development of modern imaging that that reflects the best in interdisciplinarity. And he did it much before we could even spell the name interdisciplinarity. So Britain, all I can tell you that from this tiny small podium and from the small place that I'm coming, you have been my icon for decades. So let's applaud Britain for his wonderful achievements. It's truly unbelievable. For me, it's really spine-shivering. Now let's go to the other part, to the less important one, and that's my own science. And I will not go through all the details. I'll just show you a little bit what we did and try to make it equal for every one of us as far as complexity or simplicity is concerned. And what we did when I was a graduate student with Avram Hershko in Haifa in the late 70s and early 80s, we bumped upon a problem that was completely unexplored at that time. And maybe people are asking me for secrets of success, and I always tell them that I don't know of any secret of success. But if I think in retrospect, one way to go is to go against the mainstream, against the fashion, against the expected. And I think that I was privileged to do it, maybe because I had a choice. From time to time, people have a career in which they just go from step to step to step to step, and they are being carried away. And I was already not only a physician, I was already a surgeon when I decided to leave the operating theater and to start a new career in science, so I still could always go back to operate on patients. So I picked up the subject and mostly the mentor very carefully. I had this privilege and opportunity because I can always say, well, I don't want to do it. I can go back to be a physician. And the reason that I picked up Avram as a mentor and protein degradation as a subject was very simple. I went and talked to about 10 or 15 different mentors and asked them what to do. I mean, what will be the project of my PhD thesis once I enter the lab? And everybody was awfully clear. They told me, I'm interested in that, and you'll do that, and this is the only thing that is not known. There is a tiny small corner, let's do it. And you are on a safe track. And Avram told me, I don't know what we are going to do. I have no idea. I know that maybe somewhere there is a hidden system that degrades proteins in the cell. I don't know how to attack it. I don't know what will be the biological model that we are going to take in order to ask this question and to decipher it biologically. And basically, we are going to take, if you join me, an incredibly risky pathway. And I said, I like it. I like the uncertainty. I like the risk. I like the not known. And I said, what can happen? Let's go for 2-3 years. Probably nothing will come out. And then at the end of this nothing that came out, I'll go back to operate. So I took the chance, and we are here today. Again, it's not an advice that I give you, because you cannot repeat it. I cannot repeat it myself, I think. It's a matter of luck, of choosing the right people, the right mentors, being at the right time, at the right place, working hard. Many elements to it, but all I can tell you that I picked my project very, very carefully. And at the end, I ended up choosing the most vague, unclear, and unknown route. So what was it? People at the 70s were very much interested in the translation of the genome into the proteome. This was the post-Watson and Crick splash. The DNA structure was identified, replication of DNA, the sequence from DNA to protein to RNA to protein, the road was paved, and everybody was on gene regulation and how proteins are made. Nobody cared a bit of how proteins are degraded. And people knew that proteins are degraded, but they said, that's not interesting. That's probably scavenger, that's garbage, it's the end of the process. And there was some knowledge of the field, but very scarce, and basically nobody was interested. Again, in retrospect, it acted to our advantage, because for 7 successive years, we were alone in the field. Nobody was interested. We published 12 papers. Nobody responded. Actually, our papers were kept on rejected from every journal that had an impact factor above 3. So we had to go to the very low impact. We were very lucky at that time to work in Philadelphia in the Fox Chase Cancer Center with Ernie Rose. And Ernie was at that time already a member of the National Academy of Sciences. And he said, hell with all these reviewers. We shall take your papers and put them into PNAS without any review. And hell with all the reviewers. So we circumvented the way of quality control, and we took all the garbage and put it directly into PNAS without any review. So this was the only way to go these days. And we managed after a few years to float, and it took 8 to 9 years until the first person noticed that there is some background noise and started to work about it. It was Alex Warshawski at the MIT. I was at that time at MIT, so I actually bridged the knowledge, and to him I was a postdoctoral fellow at MIT. And it took more than 15 years to the system to gain momentum and for people to start work on it. And all I can tell you now that there are more than 100,000 papers on the field, drug companies, patients, hospitals, physicians, everybody is working on this major platform. But this happened only in the last 10 years. It took us 7 years or 8 in the complete desert, then another 7 years in half a desert, and wandering in half a desert, still very thirsty, until we saw some light. So the idea is obviously to be a little bit on the stubborn side of life. So what we did, we were asking how proteins are degraded, and I'll take you very quickly through some of the principles and through some of the numbers, and why at all we are degrading our proteins. It wasn't clear at all that proteins are degraded. And I'll just give you a little bit of historical briefing. The numbers are staggering. We are destroying every day about 5 to 10% of our own proteins. 5 to 10%, which is a huge number. And once you know the number, immediately 4 questions pop up. Why we do it? How we do it? What happens if it goes wrong? And if it goes wrong, can we do something about it? Now, this is the right order of the questions. You first ask why we do it. And then you ask how we do it. You decipher the mechanism. And then you ask what can go wrong with the mechanism. And only at the end, you're going to develop drugs and to apply this knowledge to the help of human beings. If you will start the opposite way, you'll get nowhere. Because you cannot develop a drug to a mechanism that you don't know. And you cannot develop an inhibitor to an enzyme that you don't know exists. And you don't know, even if you know that it exists, you don't know the mechanism of action, and you don't know how it looks like structurally, because then you cannot design the drug that will sit in the right pocket of the enzyme in order to inhibit it, to serve as an antagonist or as an agonist for this purpose. So there is an order by which you can put the questions. From time to time, you don't have to go very regularly, very orderly, very obediently. Things mix, but generally you have to keep this track. And this is the track that also will bring at the end not only the best fruits, but the most of knowledge. So why we are degrading our proteins? We are degrading our proteins because of several reasons. One reason is quality control. Many of our proteins get misfolded. They get denatured for many reasons. One of the most important reasons, and Britton will tell you about it, is the simple fact that we are living in 37 degrees. 37 degrees is a horrendous temperature for proteins. They don't like it. Proteins in the lab want to be on ice. They want to be frozen in liquid nitrogen in minus 180 degrees. They don't like the high temperature. And the reason that we are living in high temperature without going into all kinds of arguments is probably because this is kind of an intermediate temperature that on one hand will not denature most of our proteins, like will happen at 42 degrees, that we are going to die, but on the other hand allows efficient catalysis of all the numerous biochemical reactions that make us what we are. So this is probably the end of a very complicated evolutionary process that put us at 37 degrees, and not at 34, and not at 39. Another reason is probably the oxygen in the atmosphere, that again, the 21%, that allows us to have a very efficient respiration and to utilize in a very high efficiency the energy in the different foods, to convert a large portion of it into storage material, to use the rest of it in order to generate heat. But oxygen has its bad side, and that's it oxidizes proteins and it damages them. And we have to remove all these garbage proteins. So quality control. Another reason is control of processes. There are many processes in the body that we need to control, and the way to control a process is to activate or to deactivate the protein that controls the process. Let it be the cell cycle, let it be transcription, and the best way to turn off a process is to kill the protein that regulates it. So if you want to kill transcription, you degrade NF-kappa B. If you want to kill growth stimulation, you kill the EGF receptor. You just execute it. There are other ways to do it, like phosphorylation and dephosphorylation, or ribosylation and deribosylation. So nature has found many other ways to regulate processes. And one may ask, why to destroy a protein rather than to do it in a little bit cheaper way and maybe more elegant way? And I don't have the answer to this question, but the answer may be the certainty of the process. There are some processes that you need to secure that they will be unidirectional, that they will keep polarity. And phosphorylation and dephosphorylation may slip a little bit. They may be a little bit slippery. If the process is not accurately regulated, the process that is regulated may not be tightly controlled. But if I degrade the regulator, there is no way to go back, unless I resynthesize the regulator from the very beginning. If you take a protein and you just cut it into two, there is no way to glue it back. It's gone. One single cut in a protein will completely take it away. So we need to control processes, and we need to keep quality control. Again, I want to go and to pay tribute to history of science. And the founding father of the field was Rudolf Schellheimer, a Jewish scientist that escaped Germany at the late mid-30s and worked along with Harold Urey at the Department of Biochemistry in Columbia University that was chaired at that time by Hans Clark, that assembled those Jews, including Konrad Bloch, into what you can look at as not only probably the best department of biochemistry at that time in the world, but also the very beginning of the success of American science. Science, because of the war and the Holocaust, ended the huge culture that was at that time based in Europe and moved it almost immediately with a gap of 9 years or 6 years into the United States. The United States didn't enjoy the science that it has today, and if it wouldn't have been the World War II and the Holocaust in Europe. So we need to recognize this historical landmark of time. And Rudolf Schönheimer, along with Harold Urey, did very simple experiment. They took labeled amino acid, which is the building block of a protein, fed it into an animal, and saw that the animal takes the labeled amino acid and put it into proteins, incorporates it into proteins, and then the label disappears from the protein. So proteins are dynamic. And he called this, the whole collection of his studies, he published a small book. Actually, he died at the time that the book was published by his successors, Sarah Rittenberg and others that took his work and collected it. This was a series of lectures that were given at Harvard and then the Harvey lectures. And he called it the dynamic state of body constituents. He found for the first time that our body is dynamic, that we are generating and destroying it at the same time. And he did it also for lipids, and he did it for carbohydrates, and he did it also for proteins. So he was interested in the dynamic of body macromolecules. And then something else happened, and things developed. People didn't accept this. It wasn't, people believed at that time that proteins are static, that they are not degraded. So this was a new notion that took many years to be accepted by the scientific community, but meanwhile something else happened. And Melvin Simpson in the mid-50s in Yale published a very strange paper in JBC, in the Journal of Biological Chemistry, showing that protein degradation thermodynamically, paradoxically, requires ATP, which didn't make any sense because proteins are high energy macromolecules. Once they are degraded, they should release energy rather than take energy for the degradation. So it was, thermodynamically, it was completely the opposite. And you can see here, without going into the details of the experiment, this is protein degradation. Take from it whatever you want, just a measure. Once you change the atmosphere in the incubator from oxygen to nitrogen, protein degradation ceases altogether. Mel Simpson didn't understand the experiment, and he could not have possibly understood the experiment because it took another almost 20 years for us to understand the mechanism by which energy is being consumed in a process that is apparently exergonic rather than endergonic. And then came another wonderful scientist, Christian de Dive, a Belgian-American, worked in Louvain in Belgium and then in the Rockefeller University in New York, and found the lysosome. And the lysosome is an intracellular organelle, exactly like the mitochondria that Britton worked a long time along his career on. It's another organelle, and this organelle contains proteases, which are the enzymes that degrade proteins. These are the cleaving, the cutting enzymes, and argued that the lysosome is the organelle that degrades intracellular proteins. And Christian, still alive, a wonderful, wonderful scientist. And when he asked how the lysosome is degrading intracellular proteins, he pointed out to these tiny small vesicles that are known as microautophagic vesicles that pinch off droplets of the cytosol into the cell, into the lysosome. These pinched off droplets are vesiculated, then they pour their contents into the lysosome. The contents is meeting the proteases, and all the contents are dissolved, gone. So this discovery was a major discovery in cell biology, and for 20 years or so, people again didn't think at all on protein degradation, because they said it's known how proteins are degraded. It is the lysosome that degrades intracellular proteins in addition to degrading also extracellular proteins that are coming from the outside milieu, from the outside environment of the cell, like the LDL receptor core protein, like the insulin ligand, like the growth hormone ligand, like the EGF, that are coming from the outside and going to be degraded in the lysosome. So the lysosome is the organelle that degrades everything. So for 20 years the field was dormant. And then people started to doubt again whether indeed the lysosome is the organelle that degrades also intracellular proteins, because it became clear that it degrades extracellular protein. Nobody doubted that. And I will not take you again to all the details of the doubts. I will just show you one experiment, or tell you about one experiment, and actually it's a compilation of data, and again you don't have to go into details. And look at these numbers, and these numbers represent half-lifetimes of different proteins in the cell. So some proteins, like ornithine decarboxylase, live in the cell for only 0.2 hours, 12 minutes. They are synthesized, and within 12 minutes, 50% are gone. While other proteins are living for very long, for many, many hours. This finding alone could not be reconciled based on this model, because in this tiny droplet, the long-lived, the stable, and the unstable protein are together, because this droplet contains all the cytosolic proteins, and they all go together to the lysosome, and they should all be degraded at the same time. So how is it that different proteins vary by 3 orders of magnitude from one another? It was not clear. And there are other arguments in the field, and gradually, step by step, the building, the notion, the hypothesis that the lysosome is the almighty organelle that degrades all proteins in the cell collapsed. This was exactly the point that we entered the field. On one hand, a hypothesis collapses because of negative findings and inability of people to explain very fundamental findings. On the other hand, there is no alternative, but people feel that there is something. And we felt that there is something and started our search into the new system. And I will tell you very briefly of the system, but then I'll take you directly into modern life and medicine and show you how people applied the system. So, as was mentioned in the introduction, the first paper, and apparently and arguably the most important paper in the field, was published in BBRC, in Biochemical and Biophysical Research Communication, in 1978. And this was my first publication. And there we found exactly what we wanted. But it was just the beginning. And we found indeed that if we take high-speed supernatant from cells, so there are no lysosomes there, this is a high-speed supernatant, and the cells that we used didn't have lysosome anyway, these were reticulocytes. I don't want to go into how it shows the experimental system. This high-speed supernatant does indeed contain ATP-dependent destructive activity. Without ATP, 1.5% of the protein was degraded. With ATP, 7-fold more. So this was exactly what we were looking for. An ATP-dependent, non-lysosomal proteolytic system. And now started a huge march towards understanding of the mechanism. What makes this protease or mechanism so distinct from any other known protease known at that time? Because if you think of your gastrointestinal tract, and you think of trypsin and chymotrypsin and carboxypeptidases and aminopeptidases, all those known proteases that were known at the time, they will all destroy proteins, but at the same time release energy. So in our stomach, when we eat any protein, the gastric enzymes and the intestinal pancreatic enzymes will come and destroy the proteins and generate amino acid, but at the same time will release energy. And we were upstream. We were in a pathway that consumes energy. Without energy, it doesn't work. So here is ATP, the same ATP that I mentioned at the introduction to my talk when I described to you the achievements of Britain. Now we can buy ATP in a bottle. It's a white powder. You dissolve it and you add it. You don't have to have mitochondria. You don't have to have anything. You just pay dollars to Sigma and you buy it. So the process was ATP dependent. And then we found something very peculiar. We found a very complex mechanism. It was a non-paradigmatic mechanism. People didn't think about it. I will go with you very briefly through the mechanism. The mechanism is basically a two-step mechanism. It's a mechanism in which proteins are first selected for degradation, so they are not being cut immediately. They are first selected for degradation and separated from the rest of the crowd by tagging them covalently with another protein that is called ubiquitin. This molecule of ubiquitin was called by the Swedish the kiss of death, because it kisses the protein and destines it for dying. So it's a marking mechanism in the cell that selects proteins that should die at a certain time, marks them covalently for degradation by tagging to them ubiquitin, and then the protease will pick up not every protein, but only proteins that were tagged ahead. Only what we call ubiquitinated proteins, or ubiquitin tagged proteins. Now, this was a major change in concept from many reasons. Again, I don't want to go into all the details. This is more a subject to an advanced graduate and postgraduate course. But first of all, nobody knew at the time that protein can change another protein. The protein can hook to another protein. There were some initial data about it, but it's a massive process in the cell. Nobody knew about it. People knew about phosphate. They knew about phosphorylation. They knew about ribosylation. They knew about glycosylation. But they didn't know about proteination. That one protein, a big protein, can hook to another protein. Second, it explained also a very important mechanism, and that, again, I shall use a metaphor. It explained how a shark and a bait can live together peacefully in the same room. Because in the lysosome model, don't forget that proteases are inside the membrane. It's an organelle. Here the protease, the shark, and the bait, the protein, live in the same compartment, in the cytosol. But nevertheless, one will not destroy the other. It would have been disastrous if in the cell trypsin and chymotrypsin will just float around freely, because then the cell will be destroyed. We need an intermediate mechanism of tagging, of marking, of telling you are going to die, in order for the protease to jump on the victim, to tag it, and then to subject it to degradation by the ubiquitin system. So that's how it goes. Now I'll show you a very brief animation. This is a technical, well, for me it's my life, for you it's more technical, and I'll show you what's going on. Here is the substrate, this is the victim. The victim hooks to a scaffold protein called E3, ubiquitin ligase. There are about 1,000 ubiquitin ligases in the database, 1,000 different enzymes. The ubiquitin system that we discovered, now we know, contains almost 2,000 proteins. It comprises 10% of the total human genome, by far the largest known family in the human genome. In parallel, ubiquitin is being activated by ATP. It's exactly the same way that amino acids are activated for protein synthesis. in exactly the same way that Fritz Lippmann found how short peptides are generated in non-ribosomal synthesis. I will not tell you how we followed the footsteps of history in our own track. All what we had to do is to pull out from the library the yellow pages of papers that were published 25 years before us and to copy them word by word. Very simple. You don't invent any wheel. You don't reinvent any wheel. You just follow your predecessors, the giants. Ubiquitin is activated by ATP, goes from one enzyme to another, and then goes and tags the victim. Once the victim is tagged, it's being doomed. It's being doomed by a big protease, 2 megadalton protease, huge protease, 2 million Dalton protease, called the 26S proteasome, that unfolds it and cuts it into tiny, small pieces. That's the end of the beautiful protein. So that's all what we did, these 3 slides. So I can give you a whole show, but we were stuck in the middle. I'm responsible for only these 3 slides, and even that I didn't do by myself. I did it with Avram and a wonderful mentor, and not less important, with Ernie Rose at the Fox Chase Cancer Center, a protein chemist that didn't care a bit about protein degradation, didn't know anything about protein degradation, but was fascinated by our mechanism and basically helped us to understand what's going on mechanistically. It was very difficult mechanism to decipher. It was unknown. The major problem always in science, and I am sure that you can hear more on that from Britain than from me, is once you find yourself in the dark, once you find yourself without a paradigm, with no precedent, most people will get lost. Because you cannot go to the library. Nobody described it before you. You cannot ask your neighbors because they don't know about it. You cannot ask yourself because you never heard about it before. You can ask only one, I don't know how to call it. You can ask your own intelligence what to do with it. This is where creativity comes in. Once you are left without a paradigm, you are left with yourself. So now let's go to medicine. So now we know why we degrade proteins, because we need to have quality control and to control processes. We know how we degrade proteins by the ubiquitin system. Now let's ask more practical questions. What happens when this goes wrong? When this goes wrong, we become vastly sick. It's very, very bad. And again, I don't want to go into too many details. I'll stop on one of the most studied diseases in modern medicine that started to affect China in big, and that's cancer. In the Western world, we know about cancer, I would say, for the last 50, 60, 70 years. Well, we know more, but as a plague, as an epidemic, we know only for 7 decades. In China, we know about it for less, and the reason is simple. It's not that because of people are ignorant. It's because the people at the turn of the century didn't make it to die from cancer. They died of infectious diseases at the age of 30, at the age of 40, because there was no antibiotics. Women died during birth. Soldiers died on battlefields of simple scratches and wounds. People died of simple staphylococcal throat infection, and it was only the discovery of the antibiotics by Fleming, another giant, by Waxman, another giant, that jumped our lifespan from around 30 to 40 years to 70 and more, that cancer all of a sudden will be uncovered, because cancer is clearly an age-dependent phenomenon. There is cancer in children, but number-wise, it's a small number. Most people that have cancer are, I wouldn't say old people, but cancer starts to peak at the 5th, 6th, 7th decade of life. It's clearly an age-dependent phenomenon, which is interesting by itself. Why is it that cancer starts at this age and not at the age of 5 or 10? So now, let's look at this is the ubiquitin system, and proteins, like any other parameter in the body, are degraded and kept in a steady state. They must have a level. Everything is a number in life. At the end, there is so many hours in a day, there are so many seasons in the year. Blood pressure is numbered, sodium, potassium, phosphate, cholesterol. Everything has a value. We don't live in a yes or no world. We live in a very numerical, quantitative world. So proteins have to be kept in steady state, and one of two problems can occur. Either a protein will be excessively degraded and will go below its steady state level, or the protein somehow will not be degraded and accumulate. Both conditions will lead to a disease. And again, I'll stop on cancer. I'll just tell you about cancer, and I'll use metaphors and examples at the same time. Now let's look what is cancer. Cancer is a very complicated disease. It's not influenza that is caused by a single virus that we may defeat. It's not HIV that is caused by a single virus. It's not a diarrhea that is caused by an E. coli pathogenic strain that we can treat with antibiotics. It's a multifactorial disease, and it can arise from different reasons. The normal cell is living all the time at a balance between a push to divide, between stimuli that force the cell either to divide or to activate growth pathways, and on the other hand, by brakes. So you can imagine that the cell is a very simple car, because in the car, let's leave alone the stereo system and the roof that protects us from the rain. Basically, the car is a balance between two pedals, between the gas and the brake. We cannot have a car without any of them, because if we have a car with a gas, it will run crazy. If we just brake, we'll go nowhere. So the cell is also a balance between drives to growth and division, mostly, and stop signals. And when we go from the metaphor to real biology, we are talking proteins. The cell speaks one language. It speaks the language of proteins. And there is a group of proteins in the cell that are called tumor suppressors. The best known and studied of them is called P53. Was discovered by Arnie Levine and by another Israeli scientist, Moshe Oren, now in the Weizmann Institute. And P53 is the genome guardian. It keeps the cell, it suppresses tumors. So whenever the cell has a mutation, whenever the cell goes bizarre, P53 will jump up and kill the cell. It suppresses tumors. So you can imagine what happens if P53 will be overly degraded. There will be no P53. The cell will not sense the mutation, will not sense the damage, and will keep on running and dividing as a mutated cell, and will be converted into a tumor. In the biological terms, it will be malignantly transformed. On the other hand, we have oncogenic proteins that push the cell to divide, like the EGF, like the NGF. Was discovered by Stanley Cohn, by Rita Levi-Montalcini, other giant in science. You really go and learn all those names. They are so meaningful. And each of them has, again, added enormously to our understanding of modern biology. So if an oncogenic protein that drives the cell to divide will not be degraded and will accumulate, the balance of this car will be to ride very fast. There will be more gas than brakes. So you can imagine that the cell is all the time in a balance. When there is a mutation, P53 will kill the cell. Normally the cells will be balanced and divide only when it needs to divide. So over degradation of a suppressor or under degradation of a stimulator will lead to cancer, and we know about the two situations. And I can tell you one example. For example, uterine cervical cancer, cancer of the uterus of women that is caused by human papillomavirus, is caused because the virus drives P53 to degradation by the ubiquitin system. It somehow misleads the ubiquitin system to think that P53 is wrong and the cell rids itself of a healthy, good protein. So the epithelium, the endothelium of the cervix of the uterus is now exposed to malignant transformation caused by the human papillomavirus. And in China, I assume you have a lot of those. Now there is a new immunization for the virus, so there are major developments in the field. Some types of breast cancer are caused because the EGF receptor is not degraded and keeps on signaling to the cell non-stop, and the cells keep on dividing. So we know in both extremes, we know the pathologies. Now, once we know the pathologies, the next, and I wouldn't say the last, but an obvious step, is to ask ourselves what we are doing about it. Can we cure it? Now comes the role of science as a servant or as a service platform for the people that pay for the science, for the researchers that are doing the research in the university and in research institute. This is the point when we are transforming the knowledge into a technology, into a drug, into a device that will at the end help the people for whom we all work. So now we are coming to drug. We know the mechanism. Now we can develop drugs. And I'll show you one drug that was developed by an American company called Millennium. There are many more drugs in the pipeline in different stages of experimentation. I will not go into it. I'll show you just single drug, and then I'll open the podium and then I'll end up with another personal comment, and then I'll open the forum for questions. So, to develop the drug, people had to understand, to know that there is an enzyme, to decipher its three-dimensional structure, and only then you go and design a drug. And the drug was developed against the proteasome, this catalytic machine, the scissors that cut the protein. In order to develop it, people had to understand the exact three-dimensional structure. I just briefly bring you into the three-dimensional structure without going into detail. This is a very rough resolution at several angstrom. This is a higher magnification of the catalytic side, and this is an even higher magnification of the several subunits that make the catalytic chamber. And a drug was developed. This is the drug. It's called Valcade, available in the markets in the United States, in Europe. I don't know whether it's licensed in China, but I assume it is, because it's sold all over the world. And the drug is called Valcade or bortezomib, and it's good against a disease called multiple myeloma. It's a leukemia. It's a cancer of the blood, in which bone marrow cells, that in the factory, you know that we are making our blood in the bone marrow. The bone marrow makes all the cells of the blood. It makes the red blood cells, it makes the white blood cells, the different white blood cells, the monocytes, the polymorphonuclears, the lymphocytes, the megakaryocytes. And once there is a tumor in the bone marrow, those cells cannot be formed because the tumor expands and occupies all the space, and that's exactly what cancer is all about. Cancer is a space-occupying lesion. So there is no bone marrow, and the patient is dying in agony because he dies of anemia. He cannot take oxygen. There is no hemoglobin for him to carry the oxygen because the red blood cells are not generated. He suffers from deadly infections. There are no white blood cells to protect him. He suffers from hemorrhages because there are no thrombocytes to clot his blood. And he suffers from unbelievable pain because the bones are broken, one after the other. Mostly the vertebra, because the tumor grows and grows and grows and erodes the vertebra and the log bones where the bone marrow is. A very deadly disease. Since the cells that are multiplying are plasma cells, cells of the immune system, they secrete a protein that can serve for the physician as a biomarker. So we can measure the protein in the serum and can tell how bad is the patient. This is one rare case in which Britain we don't need any imaging device. All what we need is a small syringe. We take a little bit of blood and we can tell how good or bad the patient is doing. A very rare cancer that we don't need any imaging. We can rely on biomarkers. And I can tell you also that we were talking today during the board meeting and the scientific discussions that imaging is going to contribute tremendously to our understanding of pathogenesis of disease, to our ability to see disease at early age. But side by side, the field of biomarkers is going also to develop, because we want to really diagnose at a very early age, and no doubt that all those diseases have specific attributes, specific characteristics that is reflected in unique biomarkers in different body fluids. Let it be the urine, let it be the blood, let it be the cerebrospinal fluid, let it be any other sample. So you can see here that the disease is galloping, the tumor grows. Here starts a conventional treatment, and the patient responds partially, but then the patient relapses again, and here starts the treatment with the new drug, and the patient goes into a remission, a complete remission. Now, the beauty of this drug, if you are into the cancer field, that this is not an irradiation, this is not chemotherapy with all the side effects. This is a drug that comes from a different direction. It inhibits a novel system. And therefore, not only that it's efficient by itself, but you can imagine that it will be efficient as a synergistic drug to other known conservative modalities. I don't want again to bother you and to take you into the complicated world of pharmaceutical and therapeutics, but we know as physicians, and the drug company knows very well, the difference between an additive effect and a synergistic effect. Additive effect, that you are hitting the same mechanism with a similar drug. So there is so much that you can do until you saturate the mechanism and you cannot work on it anymore. So if blood pressure is caused by several factors and you treat it only with one drug, the one drug will hit only one mechanism, but then you don't treat the other ones. If you are coming from different directions, the treatment ought to be much more efficient, and this is the case with this drug. It comes from a completely different angle, and without going into details about this patient, you can see the bone marrow, you can see the malignant bone marrow that is very homogeneous. I will not go into the details, and you can see that post-treatment, beautiful red blood cells, white blood cells are flourishing again, and the patient is completely healthy. I think I'll just bring you another one for this drug, because this is using imaging. It's another imaging. It's a computerized tomography, very important imaging that was developed in the 60s and 70s, and now everybody uses it. There is no hospital in the world that doesn't have a CAT scan, a computerized tomography. And you can see here a tumor. This is the lung, this is the air. You can see here the rib, the sternum. You can see the vertebra, the spinal canal, the scapula, the shoulder muscles. You can see very clearly the big vessels of the heart. Very clear imaging. Here is a tumor, non-invasive diagnosis, completely non-invasive, like we want good imaging to be. And following the treatment, the tumor shrunk from 2.5 by 1.2 centimeter to 0.4 by 0.4. Significant shrinkage of the tumor. Okay, I'll finish here, and what I want to do now is to take the remaining few minutes and to tell you a personal story. This was a very long route, and as I told you, I was involved, or we were involved, only in a very small, thin layer that obviously still is going on. I mean, there are thousands of researchers in the world now studying the ubiquitin system. We are far from understanding the ubiquitin system, and new questions are coming. And I want to end up with two personal stories. One personal story has to do with our appreciation and humbleness towards the complexity of nature. And there is a habit during the Nobel ceremony that there is a dinner, and during the dinner, representatives of each category of awardees, of prize winners, speak for 5 minutes. They are given only 5 minutes to speak. So what do you say in 5 minutes? You thank the king, you thank the members of the academy, you thank your wife, that allowed you not to see her for so many years and to raise alone the children, and for traveling so long. You thank your friends, your students, your fellows, and then you are left with half a minute. So what you are doing with this half a minute? A challenge. So David Gross, who won in 2004 the Nobel Prize in Physics, said something which for me was illuminating. He posed the question, and the question was, will there be Nobel Prizes being awarded in 100 years from now? In 201-4. In 2104. So people were the reaction in the audience was very strange. What does he mean that in 100 years they will award the Nobel Prize? While people are thinking about this stupid question, he immediately went into the answer. And the answer was, well, there are two factors here. One factor depends on economy, because the Nobel Foundation runs on the endowment that Alfred Nobel left behind him. And the question was whether the economists that run the endowment will be as smart as Olivia, the banker, to run the endowment efficiently, so the endowment will generate every year the expenses plus the award, because you are living on an interest. If you are doing less than you give away, you are losing. So you need to be a smart banker. David said, well, the Swedish can do it. That's easy. They did it for 100 years, they'll do it for another 100 years. No problem. By the way, Olivia, I once asked my wife, tell me with real decency, if you had a choice for the same husband, I didn't ask her to change her husband, what would you prefer, a successful banker or a Nobel laureate? Guess what she said? Obviously a banker. So then David said the real challenge is, or the main question is not the banking issue, but whether in 100 years we shall know everything, so there will be no knowledge to justify Nobel Prizes. There will be no breakthrough anymore. We shall know everything in 100 years. And the answer was no. In 100 years, we shall know less physically, mathematically, quantitatively that we know now. Because every question will open 10 new ones. 20 years ago, before the ubiquitin system, nobody asked the questions about diseases and mechanisms and enzymes and so on. Now we know much less on proteolysis than we knew 20 years ago. Basically, what he said is that the ultimate product of knowledge is more ignorance. What we are doing in our laboratories, we are the most efficient generators of ignorance. Which is interesting, think about it. It gives you a little bit of humbleness and appreciation to the complexity of the world that we are living these days in. The other personal lesson was also during these ceremonies in Stockholm, didn't relate at all to the prize. It was a reception that was held on our behalf by the Israeli ambassador to Stockholm. It was a holiday. The Nobel Prizes are awarded in December. Christians are celebrating Christmas. Jews are celebrating Hanukkah, a different holiday, but the holidays coincide. And it was a lovely party that the Israeli ambassador threw on our behalf. There are all ceremonies in Hanukkah with candle. We light a chandelier and we bless and we sing. It's a very nice holiday. And then the ambassador came to me and said, Aaron and Avram, I have a surprise for you. You know, people tell me that they have a surprise. I always think of my hobbies. Archaeology, Jewish silverware, books, records, rare music. And I'm involved in many things in this world. I'm kind of a curious searcher. So I said, what is the surprise? He said, let's see. And I was already told my wife, our luggage on the way back home will be much larger than our luggage on the way here. And the surprise was a human being. a man walked in and told us a story, and the story was very simple. He was a multiple myeloma patient. That basically, this was 2004, the drug that I told you about was still experimental. He was basically dying in the Department of Hematology Oncology in the Karolinska Institute hospital. The Karolinska Institute is the biggest medical school in Sweden and by far one of the most famous in the world. It's a standalone medical school. They don't have a university. It's just a medical school and a very good research institute. They have a very good hospital. And the patient was actually dying, and then the physicians decided to go to the last resort to this drug. It was still experimental drug, was not approved officially by the Swedish FDA. And the guy was healed, was cured at that point. It's not guaranteed that he will live long life, but he was in remission, as the oncologists say. And he was very healthy. I looked at him, I'm a physician, I said to him, Mr. Johansson, you look healthy. You shake my hand very forcefully. I look at your eyes, at the sclera, I look at your hands. You're not pale, you're not anemic. You can say immediately whether patients are anemic if you have a little sense of medicine, of clinical medicine. You're not weak. That again will emanate from anemia and from lack of oxygen. You look healthy. He said, yes, I'm completely healthy. And I came to thank him. I said, thank me for what? He said, for rescuing my life. I said, I'm not your physician. I didn't even develop the drug that rescued you. I didn't know anything about the drug. It was developed generations down the road by others. He said, yes, but without the knowledge, the very basic knowledge that you and your fellows placed, this drug could have never been developed. And without the development of this drug, I wouldn't have been alive today. Basically what he told me is exactly what I told you at the beginning of my talk. He told me that I am a small link in a chain of knowledge. I started something, somebody else came to follow me and added another brick. Somebody else came later and added another brick and another brick. And together, a chain of knowledge was generated that at the end, this patient went back from his dying bed in the hospital to his happy family. This is an unbelievable lesson for all of us. Not only for me personally as a physician, because I always thought, well, by going away from medicine, I'm going to miss the patients. I mean, the patients is the core of medicine. So now I'm going to the cold laboratories, to the test tube, to the centrifuges, to the spectrophotometer, and the tension in life will go away. So for me it was also very personal because it was a closure of a cycle. Here is a patient that I never touched, come back to thank me for curing him. But it's also a lesson for all of us how the chain of knowledge is matured at the end of the way and being brought back to those who paid for it. Thank you very much.
Wonderful story and science tonight. And now the floor is open for questions and answers. Well,
We'll take few.
okay.
Otherwise we are not going to sleep tonight.
Professor Aaron, I have two questions to ask. Firstly, the line supporting time is different for everyone in general. How long a person's life would be in theory?
I didn't get it. What was the question? Ask it in Mandarin.
First question is, the line supporting time is different for everyone
Yeah, okay.
in general. How long a person's life would be in theory?
How long a person's life should be in theory?
Yeah.
Ask Britain. I really don't know. I don't think that the phenomena are, they may be linked on the serious side, but we really don't know what is aging. I mean, aging is more, we don't know what aging is. I mean, when I was a kid, my father that was 50 years old looked to me like a very old one. Now I'm almost 60 and I feel very young. So I don't know what's age. And ask Britain, he feels even younger than I am. It's all on a relative scale.
Excuse me. One question, one person. Take some chance to others, please.
You said many years ago you were very alone in the field and nobody is very interested in your papers. But you are continuing to research in the field. What supports you to continue to research in the field? And in the end, you got the Nobel Prize.
Well, about the Nobel Prize, I'm not going to comment. It wasn't my decision, so I don't know. It's mostly internal determination and belief that what you do is right. You know, if you have a suspicion, now I'm serious. In the laboratory, we are very frequently prone to artifact. We are exposed to artifact. And they are coming all the time. And they are naive artifacts. I mean, it's not that we are involved in fraudulent, that we are cheating, that we are malicious. Students are coming, you are doing an experiment, something comes up, you don't know, you did it in the right pH, in the wrong pH, you did it in the wrong temperature, you put the wrong reagent, something comes up and you don't know what it is. You have to be certain enough that what you are doing is right and what you are doing is exceptional and has not been done before. If you believe and you know by control experiments and you attack the problem from different angles, you don't go via one set of experiments. You do it one way. You take ATP, you take ubiquitin, you reconstruct the system different ways. You gain confidence that the system tells you the right story. It cannot be that if you approach the same problem from completely different experimental angles and you get the same result, that the system is wrong. You don't do artifacts 7 times in a row. So you believe you're right, and then you continue, and that's it. You don't think of prizes. I think that prizes it's a wrong idea to think of them. If they come, they come. If they don't, life are as happy. I don't think that I'm happier today than I was 3 years ago. I'm more busy, but not more happy. For sure, happiness is something completely else. It has to do with people, with friends, with family, with whatever, with functions of the brain that we don't understand. And we are still searching for. It's just a matter of feeling in the lab that you are doing the right thing. And then, what do I care about what people say, think about me? I mean, just ignore it. If you are sure that you are doing the right thing, ignore everything else. Because otherwise, you'll never make a breakthrough. Because always you'll find yourself one way or another in a dark. It can be a big dark, it can be a small dark. You will nailed into a back alley. And you'll have to find yourself out and to believe that you have a good enough GPS to take you out of this back alley.
Okay.
Evening, sir, Aaron. So I am from Stuttgart, and you shared that your Nobel Prize with Aaron Rose and Aaron CiechanoverWhy. Yes, and I was always confused that you three, you were born to be skeptical of something, or just want to be unique, or just you want to believe that it is right to be, you live in a system that you believe it. And I just want you to share some experience of you that researching brought and share some opinions about it.
Again, I cannot give you any recipe. I really am a very bad cook. I can make maybe a cup of tea. I cannot give you any recipe. Skepticism has been my very strong attribute from wherever I remember myself. I never take anything for granted. When people tell me something, I go back and read about it. When they tell me that Wuhan was the city in which the revolution started, I go to read on Wuhan. And I want to read on Sun Yat-sen and who he was and what motivated him. I'm just in the middle of reading a beautiful biography of Mao Zedong. It just came out, and it's called The Man Behind the Icon. And you always have to be skeptical, because if you take what people tell you, most of the times it will be right, but in the critical times it may be wrong, and then it will mislead you. So if you are keeping on your skepticism as a principle, you will get there.
Good evening, Professor. My question is about the mechanism of ubiquitin mediated protein.
At last, one good question. Yes, except for how you win something you don't know how you did it.
I want to ask, what is the criterion of judging the protein which should be degraded?
Wonderful question. This is actually the $64,000 question. People will argue that $64,000, which is an old term, is nothing today. You cannot buy even a fluorescent microscope for it anymore. It's a tiny small sum. But it's the core question of the system. Whom to degrade and when? Basically, if I have to rephrase your question, is the question of the specificity and selectivity of the system. And the answer is very complicated. I'll give you just the outline of it. It's 1,000th of ubiquitin ligases that search around in the cell for proteins that have unique characteristics. And the unique characteristic can be oxidation, can be denaturing, and you ask me what's denaturation? I can tell you that denaturation may be an exposure of an hydrophobic patch of the protein that is otherwise buried inside the three-dimensional structure. It can be phosphorylation on a specific threonine or serine or tyrosine. So you need a kinase, so you are starting to talk to other enzymes. You need a stimulus that will activate a kinase, that will phosphorylate your substrate, that will be recognized by the ligase, that will then ubiquitinate it and taken by the proteasome. So all of a sudden you find yourself in a game that there are many members of the family talking together to one another in one big party. But it can be anything. And there are numerous signals in the protein that will tell the ubiquitin system this guy is to be degraded. It's oxidized, it has an oxygen on an appropriate methionine, it will have methionine sulfoxime, which is the product of oxidation of methionine, of the SH group of methionine. So you need to know chemistry. And it can be phosphorylation, it can be ribosylation, it can be denaturation and hydrophibation. It can be any of those that will be picked up by the ligase that sits aside and will take this protein for its final destination. But no doubt, you pinpointed to the centrally most critical and important, and I would argue interesting, question of the ubiquitin system, and this is also the question that most of the drug companies are interested, because they want to develop inhibitors to this exactly specific mechanism to inhibit the degradation of certain proteins that are in need, and we don't want them to be degraded. So this is no doubt the core question, the core problem of the system.
All right, let's have last two questions.
Dear Arnold Professor, I have one question. I asked you the mechanics of the center of ubiquitin proteasome pathway is sure or unsure. And do you have the next goal of your research about it?
I didn't understand what's sure or unsure. I'm unsure about everything.
The mechanics of the center of ubiquitin proteasome pathway is sure or unsure.
Can you, maybe you'll ask somebody in Mandarin and then the question will be translated again. I'm not sure I got it. I really want to answer it, but yeah, let's go ahead with the question. I want to, maybe you can really.
Yes.阿南教授，我想问一下，就是那个半素蛋白进化途径，它的机制是确定的还是不确定的
What was it?
His question is, are you sure about the real mechanism of ubiquity proteasome pathway?
I think that I'm sure about the very basic principle, and the reason that I'm sure is that there are 100,000 repetitions in the literature of the basic experiments. So I would argue that if there are 100,000 people that did it again, and there are textbooks and monographs and conferences, we don't understand still. I would say that 95% is still under the water. But the basic mechanism of tagging and degradation of the tagged proteins is clearly known. I don't doubt it, and it's based on work of 20 years of many others. It doesn't come from my own work. When 100,000 people tell you in the literature, in peer-reviewed articles, that you are right, you may better believe them.
All right, last question. No.
Good evening, Mr. Aaron CiechanoverWhy. You know, an academic master is always a philosopher, and today we come here to listen to your talk. I think we would more like to learn the philosophy contained in your talks. And we know that you are also a member of American philosophical society. And I also know that Mr. Green Chance is also a philosopher. My question is that can you give us a brief talk about philosophy and research? What does the philosophy can do to research?
Well, it's a very interesting one, and again, we can delve into it forever. The American Philosophical Society, which is basically headed in Philadelphia, is a society of about 900 people, very few foreigners, about 100 foreigners. And it's basically a thinking tank, because they bring in together people from all disciplines, from biology, medicine, philosophy, law, mathematics, literature, to think together about problems. So this is an organization. Let's don't think about you join an institute because of different reasons, or you are being elected to an institute because of different reasons. But the core part of the question is how philosophy and science go side by side, which is very interesting. And it's not necessarily that if you are guided by philosophical ideas, you are a better scientist, or the opposite. I know scientists that are cold-blooded. They don't believe in anything. They believe only in the experiment that they do. They are not religious. They don't read literature. Not only that, they don't even read science. They are guided by gut feeling. They know what to do with their experiment. You come to talk to them 1 centimeter beyond the borders, they will not talk to you because they don't know. And nevertheless, they are excellent scientists. So there is no recipe, not in philosophy, not to say in science, to become a scientist or philosopher or a mixture of both. It's very personal. And it's what do you feel about your society around you, how loyal you are to your society, to your nation, how far you think beyond your borders, and it's very personal. So in that respect, it's me, Aaron CiechanoverWhy, that lives in the state of Israel, was born, served in the Israeli army, fought several wars. You can take it as a very personal approach. It's not something that is a principle. For me, philosophy and religious is a culture, not as a belief. I don't believe in any particular God that sits in a certain address that you can talk to. It's very important because it helps me think about the society that I'm living in. I mean, and every single thing I ask immediate question. You go. I started it in Taiwan actually. When I was in Taipei, and I was exposed to the huge art of Chinese bronze. And you ask yourself, why is it that the Chinese, out of all nations, developed bronze, the cooking pots? Basically, it started from cooking. And from heat, keeping the heat in the cooking pot. How is it that the Europeans didn't go to it, or didn't do it, while the Europeans went mostly to painting during the Renaissance and so on? What affects culture? What affects the development of religions? What affects wars? Why people kill one another? Why is it that people hate one another and they kill one another, and at the end nothing comes out of it? You can take all the billions of liters of blood that were shed during the last centuries, and I can guarantee you, each microliter of this blood was shed for nothing, for vain. But you must ask yourself why all this happens, because this is a tool to understand cultures, languages, linguistics, body language, why people are different, why mentality is different, how people evolved into cultures and society, what makes them bordering one another from one another. It's truly fascinating. For me, while science is the central piece in my life, it's the main avenue on which I walk. If I have to think of my life, it's a collection of different and distinct experiences coming from complete different directions. It's music, it's painting, it's language, it's people. And science is somehow, I happen to be a scientist. I cannot tell you why, because I am not sure that I know why. I became a scientist, but I enjoy life, not because I am kind of a hedonist. I enjoy life because life is probably, life at large, and whatever I see in life is probably an unbelievable, exciting phenomenon as a whole. Because whatever you think about wine. I mean, how wines were evolved into a culture. What's the difference between good wine and bad wine? Why the French wine and the Napa Valley wine is different than Chinese wine or whatever. I mean, think about everything in life. Every tiny small detail in life has behind it a huge world of itself. You go to South America and you see the mate, how they drink the tea, the yerba tea. And then you think, oh, it's nothing. They have this and they drink a tea. But then you go into the yerba culture and you find books and encyclopedias written about the mate that until a minute ago you didn't know what it is. But it's only the going and exploring these people and culture which all of a sudden open for you a whole world. And then you ask yourself why it's in Peru and not in Jordan, and why it's in Jordan and not in China, and why it's in China and not in Korea. It's a fascinating society that we are living in. In that sense, I'm truly a philosopher, because philosophy is very widely defined. If you ask me whether philosophical principle helped me to decipher a secret of nature, I cannot point out. But I can tell you that maybe the richness of my life and the curiosity and the skepticism, which are all linked together, because skepticism leads to curiosity and curiosity leads to knowledge and to being exposed to cultures, clearly helped me as a scientist. But there are people of different talents, and I can tell you, without putting names, that there are people that can be as narrow as 1 micron, that are much better scientists than I am. And they are not being helped by all these tools. They will walk in the morning to the lab, they will not read the newspaper, they will not know in what country they live, they will not know what language they talk. In the evening they go back and they go to sleep, and they are terrific scientists. Which tells you again, that there is no recipe and you cannot pinpoint to a single component that is a key to one success or another.
All right, we're right on time. And I truly believe that we have many questions for Aaron, but unfortunately, I think he's on the very bad jet lag. And we have a whole decision today. And however, questions asked and answered in time, something that we all have to believe. If you are really interested in something, then go for it and study. Then you can tolerate the loneliness in the math. And one thing I learned while I was in prison is I was told, if you want something good, you've got to be patient. Alright? Especially for us society now, economy, business, everything, people are becoming less and less patient. Yet everybody wants something good. Well, maybe there's no such a thing that we do for you. And with that, let's thank Dr. Aaron CiechanoverWhy.